So last week, for the class, we're going to take a look at what are called vectors. So if you've taken physics, you've probably already done a little bit with vectors, and you might be familiar with what a vector is. But the idea is a vector is a way to represent two things basically at the same time. Does anybody know what a vector is used to represent? Yeah?
Direction?
Yeah, a vector tells you the direction that something's going, and it also tells you something else about it. Think about like if you were to throw baseball. Right? It might be a certain direction you could throw it, and what else could you describe about the baseball as it's traveling, besides the direction it's going? Speed. Yep. So a vector is a quantity that has a magnitude and a direction. In the particular example I gave you, the magnitude was a speed. Vectors are also used, that's an example of a velocity vector. It has a direction and it has a speed. Another type of vector is called a force vector. So force, like if I'm pushing on this table, I might be pushing on this table with a certain amount of force, and I'm also pushing on it in a certain way. In this case, I'm pushing down. Right? That's different than pulling up. Right? That's a different direction of the force. So anything that has a magnitude and a direction. So for velocity, right, you could think of velocity as like speed, how fast something is going. So if we take a look at this website that I brought up, you could think of each one of these planes as a vector. Okay? They all have a direction they're going. They all have a speed they're going. What makes these a little more complicated is it's 3D. So it might look like two planes are really, really close, but one of them could be on the ground and one of them could be 10,000 feet high. Right? So that makes it a little different. But if we click on one of these planes, so we can see where it's going, but what I want to look at is over on the right-hand side. Okay, there's the speed of the plane, 483 miles an hour. So that's the magnitude part. And then the direction, well, the direction is kind of summarized by this root, right? Now it's a plane, so it might change direction a lot as it's flying, right? So you can see, I'm not sure what all these names really mean, but you can see coordinates, and I don't know why some of them aren't showing up, but you can see compass headings here, 270 degrees, 200, 220, 216, 265. Okay, if you look at a compass, you can look at the direction and it's summarized in degrees. Not quite the same way we do degrees, right? So when we label things, we go 0, 90, 180, 270, right? That's how we do it. If you look at a real compass, north is 0, east is 90, south is 180, and west is 270. So if we go back and look at a lot of these compass headings are between 200 and 300. Okay? So if we go back and look at this, between 200, 200 is kind of like this, 300 is kind of like this. So this plane is generally traveling west. Okay? That's the direction that it's pretty much going. Sometimes it's going a little bit north and west, maybe a little bit south and west, but it's pretty much going west. And if we click back, you can see, yeah, this plane is going from, I don't know if that's Turkey, I'm not sure, but it's traveling west, and at some points it was going north and west, and now it's heading more south and west. Right? So, but it has a magnitude and it has a direction. Generally, when we do a problem, the magnitude and direction are going to stay the same. Like the speed of this plane, it might be going 443 miles an hour now. It might be going 500 miles an hour later. Right? The speed's always changing. The direction's changing a little bit. Okay? For us, we'll pretty much we'll keep the same speed, same direction for our problem. Right? So if you go back and look at this whole page, right? Each airport has to kind of control what's happening near it. Right? It has to control, okay, you can come in and land, you can take off, and there's thousands and thousands of landings and takeoffs probably happening every hour. So could think of each one of those as a vector, and that's how the computer manages it all, along with a person too, or several people. Right? But that's vectors is how you could describe all those planes, and making sure that maybe they stay a certain distance apart and stuff like that. That's one example of vectors. Okay? And the more you zoom out, I mean, you could start to see tons and tons of these planes. I don't see the button to zoom out. Usually there's like a little minus sign. Bang like this. No. Not quite the zoom out I was looking for. But, oh. So, there's a couple different ways we can represent vectors. One way is as a ray. Okay, physically actually drawing an arrow. Now, drawing arrows is okay, but and it's good at first because you kind of get to see things very, very visual. But eventually, we want to represent vectors with just numbers, right? If we want to start to be able to do things with vectors, having to draw them out every time, especially if you have to draw them to scale, it's kind of a pain. All right, so we're going to get away from drawing more tomorrow, but we'll do a little bit of drawing today. So, if you're going to draw a vector as a ray, that ray has to be able to indicate two things to you: a magnitude and a direction. Well, a ray is perfect for direction because you just look at the arrowhead, and in this case, I can tell it's pointing to the right because it's got an arrowhead on. So rays automatically tell you direction. The way they tell you magnitude is you make them longer or shorter. So if you were to compare those two vectors, we'd say they have the same direction, but one of them being longer than the other could mean that if it's an object, the bottom one is going faster. Right? If it was a force, it would mean the bottom one is pushing harder. But whatever it is, the bottom one has a higher magnitude than the top. Okay? So we have to draw it longer. Okay, so length of the arrow is your magnitude, the way it points. There's your direction. Another reason we want to get away from drawing it all the time is because once you get into 3D, it's really hard to draw 3D vectors. Easy if you've got a computer and you can kind of look at the vector and then like spin it and rotate it, and you can see it. But to try to draw 3D on a paper is hard a lot of the time. All right, so when we draw a vector, it has 2 points. It has a point that it starts at, called your initial point, and a point that it stops at, and that's called your terminal point. Now, you can use any 2 letters you want for the initial point and terminal point. P and Q are used a lot. But if you had a vector that started at P and it went towards Q, like that, you would call that vector PQ. At least that's one way you can write it. That's exactly the same notation you use in geometry for an array. Okay? PQ is different than QP. Right? If you're talking about a line, it's not. But array, yep. PQ means start at P, go to Q. QP is reverse direction. So the naming of in the order of the letters here, if you use that notation, is important. So P is the initial, Q is the terminal. Now, one reason I don't like that notation as much is because if you have to, especially if you're on like a computer or something, that's not always the easiest thing to do. I mean, how do you write a P and a Q and then put something above it? You can. It's kind of annoying though. So the other way that you can represent a vector is you can use a single letter with an arrow above it. So this isn't really telling you the starting and the stopping point. This is just giving your vector a name. Just calling it vector M. And the way you know it's a vector is because there's an arrow above it. But that still doesn't get around that issue. If you get to type that on a computer or like on a phone or something, how do you get an arrow above a letter? It may or may not be that easy to do. So what you can do is use a bold letter. In the context of this week, anytime you guys see a bold letter means that we're talking about a vector. Right? That's not a variable. A variable is just a letter we use to represent like an unknown number in an equation. That's not an unknown number. That's the name of a vector. Okay? Just looking at a bold letter doesn't tell you much about it. Okay? If you want to know more about it, you'd have to look at the picture. Okay? What does the picture of vector M look like? So in this case, you could scroll up and say, oh, it looks like that. Okay? And eventually, you're not going to have to look at a picture. We're going to be able to represent vector with just numbers. Okay, so you won't have to draw it. All right. So we're going to look at 4 operations we can do with vectors. We're going to look at addition. We're going to look at subtraction, multiplication, and more multiplication. You notice I didn't say division, because division is not something you can do with vectors. It just doesn't work. We don't do that. And I said multiplication twice because there's 2 ways to do it. So we're going to learn one way to multiply vectors on Wednesday. We'll learn a different way on Thursday. All right. So first thing I just kind of want to think about is, let's say that you were pushing on an object, right? And then your friend comes along and helps you push on that object in the same direction you're pushing. What is the object? A boulder. So it's real heavy. It needs some help. So if you're pushing on it, or a car, whatever. So you're pushing on it. Your friend comes along and pushes on it the same direction you're pushing. What happens?
Velocity.
Yeah, the force or whatever it is, the force is double. Right? If you're pushing and they're pushing, assuming you're each pushing equal, then it would double. So the idea is your force is a vector. You're pushing like this. Your friend comes along, they're pushing like that. If you take those 2 vectors and combine them together, now you'd have one like this. It's longer because you've got double the force and it's in the same direction. So the idea is if you combine 2 vectors, the answer is a new vector. Now, it doesn't always necessarily mean it's more powerful. Okay? Only if the forces are working together. Okay? Think about like if you were to throw an object into the wind, okay? Into it, fighting it. Well, you might throw baseball at 60 miles an hour, but let's say there's a 30-mile-an-hour wind blowing at you. Well, the wind is a force. Right? You threw the baseball with a force, but the 2 forces are fighting each other. So the ball is going to slow down quickly because of the wind, right? So just because 2 forces are in the same problem doesn't always mean they work together. Sometimes they fight each other, sometimes they work together. Depends on the problem. But whenever you have 2 vectors, 2 forces, 2 velocities kind of in the same problem, and you combine them, you get a new vector. Okay? Sometimes the direction also changes. Let's say there's an object right there. If you're pushing up on it, and then your friend comes along and pushes right on it, well, what's going to happen now is it's going to move up and to the right. Right? So the direction is going to change because you're pushing one way, they're pushing the other. Right? You could also cancel out. Think about like a tug of war. Right? If you're pulling on a rope and the other team's pulling and it's not moving, it's not because there's no force there. There's a ton of force there. Think about what would happen if you cut the rope. Right? Everybody would fall over because there's a lot of tension in the cable. It's just that the amount of tension pulling one way and the other way cancels out. Right? So essentially, it's balanced. Right? So sometimes that happens too. 2 forces balance each other out. Right? So let's say that we want to add 2 vectors. Okay, I'm going to call them vector v and w. The way I'm going to show you how to do it, it's going to be visual. I'm going to show you the example first, just doing it, and then I'll go back and write all the steps. The idea is, let's say you had that vector in black, and then that vector in red. and you wanted to combine those two vectors together. The way we do it is you line them up like that first. You connect the end of one to the beginning of the other, just like that. And then, if you wanted to know, well, what would be the effect? Like, let's say those are two forces. What would be the effect when you combine them together? It would be this. What's in green? So the idea is you position the two vectors so that the ending point of one of them is right on top of the starting point of the other one. Okay? That's the red and the black. So position the vectors so that the ending point of the first one is right on top of the starting point of the second one. So that's your first step. And then to get the visual, kind of get the final answer, which is what's in green, you're going to connect the starting point here to the ending point there. And that's how I got the one in green. Okay, so the final answer is found by connecting the starting point of the first one, which is the one in black, to the ending point of the second one, which in my case was the one in red. And when I did that, that's how I got the vector in green. So what's nice about doing it this way, you get a real visual. You can really see, well, what would happen if I combine these vectors? Right? And it can get pretty complicated if you've got a vector like this. So you got one like this, one like this, and then you got another one like that. And you want to know, well, what would be the direction if you combine all those together? You know, some people might be able to visualize it, but if you can't, all you have to do is connect all of them. Trying to find a nice way to connect them. Kind of on top of each other, so it's hard to see. But I connected all of them from beginning to end. And the order you connect them in doesn't actually matter. That's where I started. Follow the path of arrows. That's where I stopped. That's the final answer. So if you take all of these and combine them all together, those four at the top, it's the same as that one at the bottom. So you can connect as many as you need to. The idea is when you connect them, though, they all have to follow the same. It's like a one-way street. They all have to go the same way. You couldn't do something like this. No, those are connected wrong. Okay? You have to connect the beginning of one to the end of the next, not an end to an end. That doesn't work. Okay. So let's just take a look at adding up these two vectors. In order to do this accurately, you really need you need two things, really. You need a piece of graph paper and you need a ruler if you're really going to try to measure things and do that. So when we do it on the test, you'll have graph paper already printed on the test. Okay. So this one says to add V plus W. All we got to do to add them up. Start like that. So now that's V. The horizontal is W. And now connect where we started to the end. And that is V plus W. Now we can't really do much with that. Like we can't say, well, how long is it? Because we didn't use graph paper. We don't know the lengths of either of these original ones.
So could you do it by getting a Pythagorean here?
If you had a right angle, yep. Yep. Problem with this one is if you make the third side, there's no right angle. So let's say we just made up, don't write these down. Let's say this was 5 and this was 6. You can find the third side, but you'd have to know an angle. And that's when we did law of sines and law of cosines. So you could just think of it like a triangle. But yep, if it was a right angle, Pythagorean theorem would work. Okay. But that's all they're looking for. So what you might see on the test or in the homework, I could give you 4 choices for the answer and say, you know, which one is correct. You know? And you can usually use a little bit of common sense, like V goes down and to the right, W goes to the right. So the final answer is going to be down and even more to the right. And that's what happened there. How much more to the right? Well, we don't know. Again, we didn't really use graph paper, but we'll figure things out like that later on. Okay, let's look at this one. It's 2 vectors. Anyone think they know what's going to happen here? Yeah. What do you mean right in the middle?
The middle of your number line.
So the final answer when I draw it, can you tell me what that would look like?
Halfway down the line.
Halfway down one of the lines. Okay. Like an arrow that's half as long?
Or we cancel out.
Or it would cancel out. Anyone else think it would cancel out?
Yeah, it creates an equilibrium.
Yeah. So what's happening here is, okay, if I do it in different colors, because everything's going to be right on top of each other, the black point is where it starts. The red point is where it stops. Okay. The black point is where it starts. The red point is where it stops. What we have to do is line up where one of them stops and where one of them starts. So I'm going to line up these two. Then after that, I'm going to connect the other two. Okay. So let's do that. So let's line up this one and this one. And then when you're done, connect that one to that one. All right. So go like this. Line those up on the right. Close enough. And now connect the black one to the red one. They're the same point. They're right on top of each other. Okay. So for this one, there is no visual. They cancel out. And if they cancel out, this is what we can write. That's not 0 the number. That's called the 0 vector. Or you could write this. Either way. The 0 vector is basically the vector that means everything canceled out. Right?
So if they're the same exact size.
Yep, if they're the same exact size, but they have to be pointing opposite, okay, in order to cancel out. If you wrote this as the answer, that's not right. That's the answer you get when you do something like this. A number minus a number gives you, let's say, 2 numbers that are the same, subtract, you get 0. Okay. These cancel out, and it's called the 0 vector.
You don't have to take your stuff, just nothing, just.
Early dismissal. Work a word into that.
Alright, so
Early dismissal.
two properties we're going to look at are what's called commutative and associative. Does anyone remember what commutative means? Like not with vectors. We're going to look at that. Just with like regular numbers. Remember what that property is? Commutative. Like think about like with addition specifically. Someone give me an example of commutative property using addition. Andrew, could you give me an example? Well, think about commute. Forget the last part of the word, just commute. What does that mean? Commute? Not sure? So what does that mean if you commute? You go where? Or you just move one place to the other. I mean, if you go, even if it's only 5 minutes away, if you go from here to here, you just commute from point A to point B. So things move, right? So does that give anybody a hint at what the commutative property means? What? Okay, can you give me an example with addition? Things moving. It's the basic idea behind it.
1 plus 2.
Yep. 1 plus 2 equals 2 plus 1. Means if you move the two numbers that you're adding, if they change places, you still get the same thing. Right? Well, that also works with vectors. Okay? Meaning if you add vector v to w or w to v, it doesn't matter the order you do it, you get the same answer. Be thinking about associative, that one's hard. All right. So here's two vectors, v and w. What I'm going to do is first I'm going to add them the way they are on the left, v plus w, and then I'll switch it and do w plus v, and we'll just compare the two results. Here's v plus w. That means you put v first, and then put w on the end of it. Here's the answer for v plus w. Now, when I do it the other way, it might not be exact, because I'm not using a ruler, I'm not using graph paper, stuff like that. There's v plus w. Now, bless you. Let's take w and put v on the end of it. Okay, so now w is first, v comes second. Let's draw the answer for that. And now let's compare the two. Pretty much the same. And if you would measure things and drew it perfectly, they'd be exactly the same. So the order in which you add two vectors does not make a difference. Right, so that is commutative. Okay, associative. Does anybody remember what associative has to do with? For numbers. And it's going to be exactly the same thing for vectors. Right, let's think about that word. Associate. Right? Associative, associate. It's kind of similar. What does associate mean? Sebastian?
So like talk,
Like just talk to yourself?
no, to someone else.
Yeah.
And this would be like another vector.
Another, you talk with someone else, right? You talk, when you associate, you do it in a group. You don't do it by yourself. Okay? If you do it by yourself, that's another one. But associative means you talk, you do things in a group, right? Associate in a group. Well, in math, how do we group things together? What symbol do we use when we want to group something? Well, addition just connects two things by adding them. But if I want to group two things together, like I say, okay, I want you to look at these two and do these first. What symbol do we use to group things? Yeah, we use parentheses. So associative doesn't have anything to do with the order or moving the order. That's commutative. Look at the order here. ABC, ABC. It's the same order on each side. What's different is which vectors are associating with which. In the first one, A and B are associating with each other. They're grouped. On the right side, it's B and C that are associating. They're grouped. Okay? And the point is, it doesn't matter if you do it like what's on the left or you do it what's on the right, you get exactly the same thing. Okay. Now, again, to show this, it's not really something you can easily copy down in your notebook because I'm just going to be dragging things around on the screen. Okay. So, here's our three vectors. If we do it the way that's on the left, the grouping symbols say add A and B first. Okay. So if I take A and B and add them up, I get that. I'm just going to put that back. I'll put that over there. So that's A plus B. Now, the next part says to add C onto the end of that. Okay, so it's almost right on top of it, but I'll connect where I started to where I stopped. And doing it the way on the left, that's A plus B, and then adding C on the end of it. Okay. I don't need that. Okay. Any questions on how I got what's on the left? Now, because I did a couple additions, I had to kind of draw by hand a couple times. It's probably not going to come out as good this time as it did last time, but we'll see. Okay. Now on the right, which two am I supposed to add first on the right? B and C. So I'm going to take B plus C. B first, then C. And I'll do that. Okay. So there's B plus C. I'm done with that, and I'm done with that. Now it says to take A and add what I just did onto the end of it. There's A. There's what I just did. Put that on the end of it. And now draw that. So that's the final answer, doing it the way that's on the right. And if I compare them, they're close. They are a little off because I didn't do it perfect. But the idea is it should be the same. Okay, so that's the associative property. Now, just like subtraction is not commutative. Think about numbers. 5 minus 2, 2 minus 5. Not the same thing. V minus W, W minus V. Not the same thing. We haven't really talked about minus yet. Minus is very simple, but the properties you guys know about numbers pretty much kind of work the same here with vectors. Okay? All right, so if you have two vectors and one of them is the negative of the other, that's visually kind of like this, example 2. The negative is just there to tell you this one points the other way. Think about what a negative does in math. It makes it the opposite. It does the same with vectors. It makes it the opposite. It doesn't change the length, just points the opposite way. Two vectors that are opposites added together will give you the 0 vector. Notice I made it bold. The way I had it originally, I had 0 as a number. That's not right. It should either be bold or it should have an arrow on top of it. Because we said earlier, anytime you add vectors, the answer is always a vector. Okay. So the difference between those two vectors is the direction that they point. And more specifically, what did I just say? If you put a negative, it makes the vector point how compared to the original? What is the difference in the direction that these two point, like specifically? Yeah, opposite, exactly opposite directions. If one points up, one points down. Perfect. All right. How about their magnitudes? If you measured the length of V and the length of negative V, how would the length of them compare? They're exactly the same. Okay. So direction was opposite, length is the same. All right, so how do we subtract two vectors? Well, I'll show you how we're going to do it. Let's say that I wanted to show someone how to do 3 minus 2. Right? They've never seen minus before. They don't know what it means. But they know all about addition. They know how to add anything. Positive numbers, negative numbers, fractions, decimals. They know how to do all kinds of addition. They've never really heard of subtraction before. How can you rewrite 3 minus 2 as an addition problem? Yeah? Exactly. 3 plus the opposite of 2. Right? If you know how to add negative numbers, then yeah, you really already know how to do subtraction, even if you've never called it that. Well, if you know how to add vectors, then you know how to subtract vectors. It's exactly the same idea. To subtract two vectors, what you're going to do is find the opposite of the second vector. Remember what we just said about opposite, which means you flip the direction, and then you add. So to subtract two vectors, find the opposite of the second, and then add. And how do you add? Well, that's what we just did. Connect the beginning of one to the end of the other. Go from there. Okay. Let's try an example of that. So they want me to do V minus W. And again, the V and the W should look bold. At this point, you guys know I'm talking about vectors, so I mean, it's understood that those are bold, but they will be bold in your homework. All right. So there's V, and there's W. What's the first thing that I have to find here to do V minus W? Something I've got to do first. Yeah. Yeah, I need the opposite of W. Okay. Well, on the smartboard, it's pretty easy to do. All I have to do is make a copy of it, and then if I reflect it horizontally, and then reflect it vertically, that's exactly the opposite. Perfectly opposite. Not roughly the opposite. It's as good as you can get. So there's negative W. All right, so I've got that. So now, how do I want to think of V minus W? Instead of V minus W, I want to think of it as, yeah?
Plus negative W.
What plus negative W?
V.
Yeah, V plus negative W. Well, you've got V at the top, you've got negative W at the bottom. Just add them up. V plus negative W. And there's your answer. That's V minus W right there. Questions on that? So subtraction is pretty straightforward as long as you know addition. All right, next thing. It's called a scalar product. What does it mean to scale something? Or think about, like, what does it mean if you have a scale model? Yeah.
All the dimensions are the same, moved up or down.
Yeah, proportionally, everything is proportional to each other. It's just a smaller or larger version of the actual object. So, for example, if you had a blueprint for a house, it might be a scale plan that's scaled down because you need a smaller version to be able to see it all, like on like a table. Versus maybe if you were in biology and you were making a diagram of a cell, right? It might be a scaled up version because cells are very small and you want to see it larger, so you draw it larger. So the idea here is we're going to be scaling a vector and it can change its length. So for example, here's what a scalar product would look like. 3V. That means take vector V and triple it. Make it 3 times as long. So when you multiply a vector by a number, we call that number a scalar. The scalar controls how much bigger or smaller it gets. Now, what kind of number do you think you'd have to multiply to make the vector bigger? Yeah. Anything larger than 1 is going to make the vector bigger. How about what would make the vector smaller and keep it pointing in the same direction? Yep. And keep it pointing in the same direction.
Anything between 0 and 1?
Yep. Anything between 0 and 1. Now, what would happen if you multiplied by a negative? Like, let's say I multiplied by a negative 3v. What would the negative do? Yeah?
Direction.
Change the direction. So when you have a scalar in front of a vector, there are 3 things that can happen. It can lengthen the vector, it can shorten the vector, or it can also flip the direction. Those are the only three things that can happen. It can't just change it to a random direction. It can only flip it the opposite way if you multiply by a negative. So Anthony, if I look at the first one here, 2v, is that going to lengthen the vector, shorten the vector, or flip it? Yeah, that's going to lengthen it. And the easiest way, if I want to find 2v exact, is just take v, and then take another copy of v, and add them up. That's 2v, once I draw it. So 2v is exactly twice the length of the original. Matt, how about 1/2 v?
1/2 v.
What's going to happen there? What about the direction? Same. Yeah, there's no easy way for me to do 1/2. I just have to kind of estimate because I don't have any graph paper. But that's 1/2 v. All right. Let's try these two. Now, if you put -1v, that's the same as -v. Same. Isaiah, what's going to happen to the magnitude when I do -v compared to v? What was my question again? What's the how do you visualize the magnitude when you're looking at that arrow? It's the what arrow? No, those are just the 2 points. The magnitude of that arrow is its what? Want to help him out? What's the magnitude? Oh, Steve? It's the length of it. Yes. So now my question here is when I say what's going to be the difference between the magnitude here and here, what's the difference between the lengths? There isn't. These vectors are going to have exactly the same magnitude, but the negative is just going to cause it to flip. This time I'm not going to try to flip it and be fancy. I'm just going to draw it by hand. Okay. So there's -v. All right. How about Brianna? What's going to happen with -1/3 v? So we did -v. We know what the negative does, but now the negative has a 1/3 with it. It's going to flip and get shorter. How much shorter? 3 times as short. So I'm just going to take the one I have right here and just kind of estimate where 1/3 would be. Right, so it flipped it and it got 3 times as short. Okay, any questions on that? All right, let's try one of these and then look at the last thing. So 2v plus 3w. Here it's just combining what we did before, addition, with a scalar product of each one. So Jason, if I want to do this one, what's the first thing I need to find to do 2v plus 3w?
The magnitude. Aren't they double, triple? Or
You don't need any actual numbers.
we have to make it longer then?
We have to make it longer, right? We got to find 2v. So let's start with that. All right. We want to make it longer, not make it disappear. All right. So there's There's 2v. All right, so I've got the first part. And now, what do I need to add onto the end of 2v? Oh, What does it say to do? What are you adding onto 2v? 3 of the w's. Okay, so take the w, make 3 of them, and just put them on the end. There's 2v plus w. There's another one, and one more. So this is the part that gets kind of annoying with drawing them out to find the answer. Is if it said like 20v plus 100w, you need a pretty big piece of paper. So there's a better way to start to do this than to actually sketch it every single time. Right? But for small ones, it's okay. All right, so I've got that. Now, Megan, what do I do to get my final answer?
Connect the.
Yeah, connect where you started to where you stop. And that is 2v plus 3w. Okay, so combining addition with a scalar product. All right, so we've been talking a lot about magnitude. When we start to get into numbers more tomorrow, we're going to want a symbol for magnitude. That's the symbol for magnitude. It's kind of these double bars around the vector. Now, since magnitude is the length how long the arrow is, can't be a negative number. Magnitude is always a positive number. So, keeping that in mind, I want to know the difference between those two magnitudes. What's the difference between the magnitude of x and the magnitude of negative x? Yeah. Nothing. Those magnitudes are exactly the same. What is different is the direction they point. But that's like measuring the distance from here to the door, or standing at the door and measuring to here. It's the same distance. It's just one's one way and one's the other. So the magnitude of x and the magnitude of negative x are exactly the same. No difference. Now, when you measure the length, if the length comes out to exactly 1, then there's a special name for that vector. It's called a unit vector. Just like when we studied unit circle. We talked about a circle that had a radius of 1. We called it a unit circle. Well, the word unit in math usually means 1. So if your vector comes out 1 unit long, exactly 1 unit in length, then it's called a unit vector. Okay, we're going to talk a lot more about unit vectors tomorrow. Also, tomorrow and probably the rest of the week, there's not as many terms each day. Today we had a lot. Unit vector, initial point, terminal point, and all these different terms. Commutative, associative. There's not as many the rest of the week. Okay. So this is the point where we don't get into it a lot today, but we're going to start to get away from always drawing a vector. Okay? You want to add vectors, especially if they're really big. We don't want to have to be sketching things. Okay? It's a lot easier if we could just use numbers. There are 2 ways that we're going to learn how to write a vector besides drawing it. This is one. And our book calls this this format an algebraic vector. So the way it looks is you've got these brackets, A comma B, and another bracket. Now, some people might look at that quick and say, well, isn't that just a coordinate? But how come this isn't a coordinate? What's different? Yeah, they're not parentheses. Big difference, right? You put parentheses, you're talking about a point. You put these brackets like that, you're talking about a coordinate. So what's the A and the B? The A and the B are what we call the horizontal and vertical components of the vector. So what do I'm going to come right back to that. I want to show you what I mean by horizontal and vertical. For that, I need a piece of graph paper. let's say we start here, stop here. There's a vector. Okay? And you want to describe that vector. This is the horizontal. Like that. It's 1, 2, 3, 4, 5, 6. That's the horizontal. And this is the vertical. 1, 2. So that vector in red is the vector 6, 2, meaning it has 6 horizontal units and 2 vertical units, basically to travel from the beginning to the end. You can think of the 6, 2 as it's like a direction. 6 units right, 2 units up, and you will go from the beginning to the end. So from the beginning, A tells you how many units to go left or right. And it's kind of like a coordinate in the sense right is positive, left is negative. And B tells you how many units to go up or down. I guess I was going to show you an example in a second. Okay, so A and B are like directions. From the initial point, left and right, and then up and down. So, let's say I want to sketch that vector. What this notation does not tell you is where to start. You can start anywhere you want. You could go like this. Start here. Go 2 right, 3 up. That's a perfectly fine sketch of that vector. You could start over here. Go 2 right, and 1, 2, 3 up. It's fine too. You can start anywhere you want. Now, there is a point that is probably the most common starting point, and usually we do start from this point. You're not wrong if you don't, unless they tell you to. But does anybody have a guess what point is the most common point to start from? Yeah. The origin. Okay, there's nothing wrong with those other ones. But usually we start from the origin. And if the vector has its initial point at the origin, that is called a position vector. And the last thing I'm going to show you, very simple, is how to get a position vector. And I'm going to scroll back up and use the grid I have right here. So we already know the answer. The answer is 2, 3. Okay, so normally you wouldn't know that. But let's say I gave you this. I gave you the vector that you see on the board right there. Right? And maybe I didn't even give it to you on a grid. Okay? All I did was give you coordinates. Let's write the coordinates. What's the coordinates of the initial point? Mm-hmm. 4, comma what? 2. And what's the coordinates of the terminal point? 6, 5. So what you might see on a test is something like the coordinate of an initial point is 4, comma 2. The coordinate of the terminal point is 6, comma 5. Find the position vector. Okay. Now, we already know the answer. It's 2, comma 3. But knowing that answer, does anyone see how you could work backwards from knowing those 2 coordinates and get a 2 here and a 3 there? Yep.
You have to go to the left 4 and down. Yes, you.
So let's say I just gave you like this. I mean, I know what you mean, but I'm trying to think of like some numbers, some like arithmetic you could do. This is the end. This is the start. Somehow figure that out. So now you have no graph to look at. Yeah? Subtract them. What what minus what? End minus start, or terminal minus initial. 5 minus 2 is 3. 6 minus 4 is 2. So, very, very easy to find a position vector if you are not given it. Okay? What you would be given is the initial point and the terminal point. Now, a lot of times what they do for the coordinate is they call them P1, P2. If they don't tell you which one is which, you always assume P1 is initial. Think of 1 as first, 1 is at the beginning, 2 is after, comes at the end. Right? So P1 is always the initial, P2 is always the terminal. Okay, so all we have to do to find a position vector, exactly what Emily said, subtract them. End, or terminal, minus initial. Do that for the x's. Terminal minus initial. Do that for the y's. Put the brackets, put a comma between it, and that's your vector. Okay, so the last one we'll finish up just by finding a position vector, and I'm going to give you guys 2 coordinates. And remember, assume P1 is the first, the initial, P2 is the end. Okay, so the directions say find the position vector. Okay, what am I going to subtract to get the number before the comma, the first number? So let's take a look. X's, yep, 4 minus -1. If you do it the other way, if he hits a -1 minus 4, you're going to get the vector that goes the wrong way. It's going to be pointing the opposite way that it should. It'll be the right length, but it'll be flipped around. So Isaiah, what is 4 minus -1? Yep. Get 5. And how about my y value? Yep, 6 minus 2 is going to give me 4. So if you were to sketch that vector starting at the origin, you would go 5 right, 4 up, and that would be where you'd stop. That's your terminal point. Okay. Any question on how we got 5, 4? All right. So, homework for tonight, it's all evens except for number 1. I think number 1 is like a fill in the blank. It's like a vocabulary question. And then 8 to 22 even, 26 to 32 even. Now, on 26 to 32, if you read the directions in the book, the directions won't make sense because they're asking you to do something I haven't taught you yet. All I want you to do on 26 to 32 is find the position vector. That's it. They're going to say something about i's and j's. We're going to do that tomorrow. So just find the position vector.